Hello friends, from all the previous video, we have taken a knowledge of impulse momentum equation and their related terms. In this video, we will see momentum correction factor and its necessity. So let us move on to the video. The derived impulse momentum equations in terms of mean velocities of the flow are based on the assumptions of the velocity of the flow at each section is uniform. That is, the velocity is same at different points on the same section. However, in actual practice, the velocity is not uniform all over the cross section of the flow passage, on account of which the momentum flux computed on the basis of the mean velocity of the flow at any section is not equal to the actual momentum flux flowing through the section. The actual momentum flux flowing through any section may be obtained by integrating the momentum flux flowing through the different elementary areas of the cross section. Thus, if v is the velocity of the flowing fluid at any point through an elementary area small dA of the cross section, then the mass of the fluid flowing per unit time is rho into V into dA, and the corresponding momentum flux flowing through this elementary area is rho into V square into dA. The total momentum flux flowing through the entire cross section A, which is equal to integration of rho into V square into dA, which is equal to W upon G into V square into dA, which may be evaluated from the known velocity distribution at the cross section. It is, however, more convenient to express the momentum flux flowing through the any cross section in terms of the mean velocity of the flow. But the actual momentum flux is always greater than that computed by using the mean velocity of the flow. Hence, there is a difference in the actual momentum flux and the momentum flux by using the mean velocity of the flow. Now, it is very necessary to convert the actual momentum flux by using the mean velocity of the flow into the actual momentum flux. Hence, in order to account for this difference in the value of the momentum flux due to the any non-uniform velocity distribution at any cross section, and the factor is called as a momentum correction factor. It is represented by the Greek letter beta, so that the momentum flux computed by using the mean velocity v may be expressed as beta into rho av square, and it is then equal to the actual total momentum flux flowing through the entire cross section. Thus, equating the two, the value of the momentum correction factor may be expressed as multiplying factor, that is a momentum correction factor beta into rho av square is equal to the rho integration with respect to area A v square into dA. From this equation, we get here beta, that is the momentum correction factor, which is equal to 1 upon av square integration of v square into dA. This is our equation number 10. Mathematically, the square of the average is less than the average of the squares. See here, mathematically, the square of the average is less than the average of the squares. That is, v square is less than 1 upon a integration of v square into dA. The numerical value of beta will always be greater than 1. The actual value of beta, it depends on the velocity distribution at the flow section. If the velocity is uniform over the entire cross section, then the beta is equal to 1. That is, uniform velocity flow is there and the velocity is uniform all over the cross section. Here the beta is 1. For the turbulent flow in the pipes, the value of beta, which lies in between 1.02 and 1.05. However, for the laminar flow in the pipes, the value of beta is 1.33. In view of the above discussion, if the velocity distribution is non-uniform, then the momentum correction factor will be required to be introduced. In the impulse momentum equations, which is expressed in terms of the mean velocity at each section. Thus, equation number 5, 7 and 8, we already learned these equations. Now we are modifying this as summation of fx is equal to rho into q in bracket beta 2 into v2 suffix x minus beta 1 into v1 suffix x, and summation fy is equal to rho into q in bracket beta 2 into v2 suffix y minus beta 1 into v1 suffix y. Similarly, summation of fz is equal to rho into q into bracket beta 2 into v2 suffix z minus beta 1 into v1 suffix z. These are our equation number 11, in which beta 1 and beta 2 are the momentum correction factors at section 11 and section 22, which is section 11 and section 22 is as shown in figure number 1. However, in most of the problems of turbulent flow, the value of beta is nearly equal to 1, and therefore it may be assumed that it is 1 without any appreciable error being introduced. Accordingly, the impulse momentum equations for the three reference directions, that is x, y and z, it may be represented by equation number 5, 7 and 8, that is summation fx is equal to rho 2 into q into v2 suffix x minus rho 1 into q into v1 suffix x. This is our fifth equation. Summation fy is equal to rho 2 into q into v2 suffix y minus rho 1 into q into v1 suffix y. This is our seventh equation, and last one is summation fz is equal to rho 2 into q into v2 suffix z minus rho 1 into q into v1 suffix z. This is our eighth equation.